and I'm delighted to introduce our speaker today, Dr. Nathan Kutz. Nathan is the Boeing Professor of AI and Data-Driven Engineering in the Department of Applied Mathematics and Electrical and Computer Engineering, and Director of the AI Institute in Dynamic Systems at the University of Washington, having served as Chair of Applied Mathematics from 2007 to 2015. He received his bachelor's degree in physics and mathematics from the University of Washington in 1990, and a PhD in applied mathematics from Northwestern University in 1994. He was a postdoc in the Applied and Computational Mathematics program at Princeton University before taking his faculty position. Nathan has a wide range of interests, ranging from neuroscience to fluid dynamics, where he's integrated machine learning with dynamical systems and control. He's also the author of hundreds of journal and conference papers and has authored multiple textbooks, including one of my personal favorites, Data-Driven Science and Engineering, Machine Learning, Dynamical Systems, and Control. Today, Nathan will be giving a talk titled Shallow Recurrent Decoders for the Automated Discovery of Physical Models, although I think we've got a different title slide today.
That part, no, I that's what I'm going to do. Is your title's right. I think in all the confusion there, I had the wrong. I had started on the wrong slide, but we're good.
No worries, no worries.
Yeah.
So you can turn your camera on as well and begin the talk when you're ready, Nathan. So join me in welcoming Nathan Kutz for our talk today. Thank you, Nathan. Take it away.
Awesome. Great. Hey, so are you not seeing me?
No,
on the
no,
camera?
You're not on camera at the moment.
Okay, let's see. Am I screen sharing? There we go. Video.
You are screen sharing. Yeah,
okay,
there we go.
Can you still see me?
Yes, we can still see you.
Okay.
And you can,
all right.
okay.
Perfect.
We're good to go.
All right. So ignore the title, but there will be definitely machine learning in this talk and doing science. So yeah. So thank you for coming. By the way, I'm at the University of Washington, as mentioned, and as of Monday, I'm actually taking a leave of absence. I'll be joining Autodesk Research in London. So if you're in London, come by and see me, and we can go on a pub run. And so that's think about that for anybody over on the other side of the pond. So I want to start here with the talk. One of the most foundational changes mathematically to the world came from Newton when he developed the concept of a derivative. And so calculus was born in 1687. Before this time, what we had was geometry and algebra. So everything was expressed in terms of geometric relationships. Even if you look at Newton's Principia, you'll see the legacy of geometry in what he developed there. A lot of what he did in explaining calculus was sort of from a geometrical point of view, because that is in fact how people really expressed and shared the world. But with the definition of derivative came a monumental change in how we could talk about science and relationships in science. In particular, what we did since that time is we've developed theories for electromagnetism, quantum mechanics, fluid dynamics, elasticity, all of which can be expressed as relationships among derivatives. And with this, we have developed amazing technologies, from iPhones to cars to rockets, all from having these first principle models which express relationship among derivatives for quantities of interest in how they change in time and space. And so this has been such a amazingly successful way for us to think about physics. The other thing I want to highlight here is look how compact these relationships are. And if we take Maxwell's equations, right, we can express all electromagnetic phenomena as, as this system of 4 equations, 4 PDEs. And this is really quite remarkable, right? People print this off on a T-shirt, and it expresses something very fundamental about the nature and that we live in. And so we have these really compact relationships, but something interesting has also happened over the past, especially since we had computing. So let's call this from the 60s onwards. We took this and we started to compute and started to, instead of solve these things analytically, we started computing solutions to this. And there's 2 big challenges that come up from this. One is, how do we estimate derivatives? Because this is all relationships among derivatives. And especially if we go to the data-driven world, estimating derivatives is actually quite difficult. And it's non-trivial. You think that'd be a very easy thing to do, but it's actually estimating good derivatives is a very difficult thing to do. And the second thing is scale. So thinking about large-scale computations, and when we and I'm going to show you a picture of this in a minute, is one of the things that we're facing now. So we have these very compact relationships, but then when we go to solving, let's say, something interesting, like here is the McLaren Formula One car, MCL39 from this year. I worked with McLaren on this car back in when I was on sabbatical in London about 2 years ago, and you can actually buy this mesh off the internet. And once you have it, you could put it into one of these packages, like for instance, OpenFOAM, and you can start doing simulations of this car. So PD Solve is a very mature technology, unlike when I was in grad school. So just in the 30 years or so since grad school, what has happened under computational technologies has been hugely transformational in terms of our ability to do science. And so this reflects here kind of where we are in the modern world, which is you can do the simulation, but you traded out Navier-Stokes for now a system that's parameterized by a 1.4 billion dimensional mesh. And so we went from something that was extremely compact to something now that is at massive scale. Okay. By the way, you can't get around this. Even if you want to say, well, I'm going to live in the data-driven world, and so I collect, for instance, data here. This is a, let's say, 4K video of flow around the cylinder, and each frame of this is 24 million pixel points. And so you're still in this high limit of data. And one of the things I want to point out here is that if you look at this, this is clearly not 24 million dimensional. In fact, if you look at the dynamics here, there's clearly some underlying low dimensional structure. And so somehow the pixel space that you used is a terrible coordinate system to represent this physics. And so part of what we're trying to do is figure out, how do I do a better job of representing these very high dimensional systems in some coordinate system so I can make meaningful physics models out of them. So this is really going to come down to thinking about latent spaces. And I think this is probably the most important step, in my view, of thinking about physics models, is constructing a good set of coordinates or observables to represent dynamics in. So how do we know we can do this? And how do we know we can maybe have multiple ways of representing this? I mean, this was really something that Einstein covered in 1916 when he was talking about the nature of governing equations is you can change coordinates and equations and they should still represent the same manifestation of what you're observing. And so this was sort of formally written down by Einstein in 1916 when he was doing studies of special relativity, which led to general relativity. And this is the first time we have this formal idea that if you change a coordinate system and represent the equations of motion, at the end of the day, they should all collapse down to the same thing. So, but it's important that you have to have equations and coordinates pairing. And so really the task here is to think about coordinates, okay? So let me give you an example of a coordinate system and to tell you that I think this is a great weakness for humans, finding good coordinates. And I'm showing you here the pendulum. So the pendulum, like the wheel, is probably something that we can't ever, nobody invented the pendulum, somehow has always been there as an observational thing. But all the way back from Euclid in 300 BC, we had all that we needed to represent theta as the right coordinate for that pendulum. And in fact, when Euclid wrote the Elements, this was sort of a summary of all the things we knew in geometry, probably for the preceding many centuries before that. But it wasn't until Galileo in 1588 that finally said the right coordinate for the pendulum is theta. And once you have that coordinate, then there's all these interesting things that come out of it. Like, for instance, that the period is equal to the inverse of the square of the length. And so you have all of a sudden the ability to understand the pendulum in a brand new way. And just think about how easy the pendulum is to understand. And yet it took, if you look here, almost 2,000 years to just get this coordinate right. So you can imagine how hard it is for us as humans, for us to actually get coordinate systems. So anyway, I would advocate that this is a story for us to say that this is one of our weaknesses, I think, of finding good coordinate systems. And so we're going to rely on machine learning to do it. So by the way, here's a kind of a prototype of what machine learning might do for finding coordinates. I can take observations of the night sky, And here you see already a machine learning idea of how to do this, which is use an autoencoder to go into a latent space and come back. And in that latent space, you could write down one model, which is the Ptolemaic model of essentially the Earth at the center, and then you have circles on circles. In fact, one way to think about this, this is the earliest Fourier transform, right? Because you're writing the planetary motion as a set of amplitudes and frequencies that you add together to describe the motion of the planet. A second model, and so you can see there's not a unique way to represent this, is to come into this, and the latent space is in fact now this geometry, which is the heliocentric model, where you have F equals ma as the dynamics. And these are two possible models that this architecture could learn, both which are very advantageous for us, okay? And so that's something we want to make use of. And by the way, they're all approximations because, in fact, here's where we live. So the Earth or the Sun being the center is kind of irrelevant. Clearly, neither of them are the center. This is at least what we know of the Milky Way where we live in. And so what they really are is just ways to approximate a model. And so I just want to say that there's nothing exact here. It's always going to be approximations. And in fact, if you come from an engineering background, what you know is if you took statics or dynamics, the entire goal of the course, step one, is to get the right free body diagram. In other words, get the right coordinate system. And if you can't get the right coordinate system written down, you're never going to solve the problem, or you're certainly not going to do it easily. So this idea of good coordinates is absolutely critical for us if we're going to do good science and engineering. Okay, and so here's the architecture we're going to use to go after this. This is something that I've been developing over the last few years. It's a shallow recurrent decoder architecture, so we're calling it SHRED. And what the network does is it maps measurements. For instance, here, this is a spatial temporal system. The red dots represent sensor measurement locations, and it goes through a time pipe or a sequence model, so something like LSTM, a GRU, RNN, something like this, so some kind of sequence model in time, and the latent space of that decodes back to the full state space. In other words, if I want to write it here at the bottom, you see that the F is some neural network that maps a sequence of sensor measurements to the full state space. And so initially when we developed this architecture, we were thinking about it as essentially a sensing paradigm. But since that time, it's grown much further and beyond this because there's a lot you can do with this architecture. And in fact, the architecture itself takes advantage of three really key principles mathematically. So when I show you the results that come about from this, I think they're quite impressive. But I'm going to also say that it shouldn't be surprising because the things that this SHRED architecture takes care of is it takes advantage of is separation of variables, Tockin's embedding theorem, and a decoding only strategy. So there's no inverse computed. So let me walk through those because those are essentially things that we use all the time in science and engineering. So let's talk about the first one of these, what SHRED uses, which is it's a generalization of separation of variables. So the way you think about it is the sequence model up front for the sensing is your time pipe, and that decodes to the spatial pieces. So it's kind of time and space are separated into these two pieces of the neural network architecture. By the way, the first separation of variables that we used for solving differential equations was by Leibniz in 1691. That's how old this idea goes. In fact, Leibniz in 1691, we know this because he wrote a letter to Huygens and where he showed how to solve a differential equation. In fact, if you've had differential equations, the first day of class, you probably actually solved it with separation of variables. And that was Leibniz's technique that he wrote to Huygens. And since that time, Fourier in the 1800s and generalized this concept for solving partial differential equations by doing separation of variables. This architecture is also largely what we use when we do scientific computing. In other words, when we solve large-scale spatial temporal systems, we typically discretize in space, and then we march forward in time. And so there's implicitly or explicitly a structure of separation of variables. So that's one thing we're taking advantage of. The second is a decoding only strategy. I worked quite a bit on this kind of architecture I'm showing you here, which is encode into a latent space, decode. And some of you may be in favor of that, but I'm going to tell you that I've done completely away with this architecture, and here's why. You can actually make this work, but you're in for a heck of a ride when it comes to hyperparameter tuning. So, and the reason is pretty obvious when you back away from it. When I come into the space and come out, you're essentially, they're inverse pairs. And the one thing we've known since the earliest days of scientific computing is don't compute a matrix inverse. So when we just do it in a linear case, what we know is computing an inverse is an ill-posed operation. And you don't get around that by building an autoencoder. The autoencoder is still computing inverse pairs, and this is highly opposed. And we've known this from the earliest textbooks in scientific computing. They just wrote it in there. And in fact, MATLAB, which nobody seems to use anymore, but MATLAB used to complain if you ever said inv A, it would actually give you a warning and say, please don't do this, right? Because they knew like this is just a dumb thing to do when it comes to scientific computing. And okay, I'll say it, but don't take me too seriously. But it's also, I think, a dumb thing to do if you're going to do an autoencoder decoder. If you can do a decoder only strategy, you do that. You get away from computing inverses. Finally, the last thing we're going to take advantage of is what's called Tauken's embedding theorem, which is a theorem from Tauken's dynamical systems theorem from Floris Tauken's from 1981. And in many ways, this theorem is sort of sat in the background as kind of like a fun math trick, but completely unuseful until I think very recently when people realized that what Tauken's did here was actually just really transformative. And what it says is if I take a dynamical system, here's like the Lorentz attractor, 3x3 nonlinear ODE. If I take one of the variables, x1, and I look at its time delay embedded version, in other words, instead of having access to x2 and x3, I just have a time delayed version of x1, then the dynamics of that time delayed version is in fact diffeomorphic to the original variable. So I don't even know what x2 and x3 is. I just know that I have a model that's diffeomorphic to the original model. Now, the interesting thing here is with training data, we nailed down this diffeomorphism. That was one of the things that Tauken's could never tell you is how you get this diffeomorphism. Nobody knew how to an algorithm to do it, but now we have a training data set which allows us to pin this down. So those are the three key factors, and let me show it to you in a simple example, a linear example. So this is just showing you how this might work in a linear case. So let's take a linear PDE, something like this. U dot equals LU. Well, L is a linear operator. So when we first learn PDEs, we typically learn linear constant coefficient. And so this is what we might have here. And in fact, when I was 20 years old, I took my first PDE course. And what I'm going to show you here was the first day of class. So it's not even sophisticated PDE theory. It's just how do you solve a PDE? Well, the first day of class, I learned this: separation of variables. Write it as a product of time and space, plug that in, and you get two ODEs. And of course, you had ODE course before PDE, so now you solve each ODE. The solution to this is an exponential. Solution to this is an eigenvalue problem, so you solve the eigenvalue problem. And when you have those, you construct a linear superposition of solutions, which is the eigenfunctions and their exponential time dynamics. And the only thing you don't know is the coefficients A of n. So that's the first 30 minutes of, let's say, a PDE course that you might have. Okay, now the next 20 minutes, you say, well, how do I determine the A of n? You solve what's called the initial boundary value problem. So what you do is you put in an initial condition. Let's say at time 0, I know the solution. You plug that into the solution form, and you take inner products with the eigenfunctions, and then that determines the A of n uniquely. So now you have a unique solution, and all this you can work out with the first day of a PDE class, okay? But there's one thing that we didn't do in the PDE class, which is obvious you can do, which is the thing I didn't know was the A of n. So what if I solve instead of the initial boundary value problem, I solve the sensor boundary value problem? In other words, I have a fixed sensor location, and I have a series of time measurements at different times and points. So the initial value problem, you know the solution all at one time. Here, I have a set of measurements over time. And if I do an n mode expansion, then if I have n measurements in time, that gives me enough information to construct an n by n matrix to solve for the A of n. That's also how I get unique solution. And that's exactly what shred does in the linear limit. And of course, we're going to take this and generalize it to a nonlinear. But that's the underlying idea. So there you go. That's the theory behind it. And so let's go ahead and now start to implement the shred architecture. Okay, so here it is. We now take this generalization from a linear model to nonlinearity in both the sequence model, nonlinearity in the decoding. And this is the original work was by Jan Williams, who is a PhD student graduating this year. And so we were thinking about it as a sensor problem. So here's your sensor locations, those dots. Here's what they look like. They come through here and you map it to the full state space. And here it's being done on isotropic turbulence, for instance. So we took this and we built this technology up, showed it was very effective for a sensing strategy. We could even have mobile sensors. And now we started using it for dynamics. And this is where I'm going to introduce to you Matteo Tomasetto, where we started doing model reduction with it. So here's Matteo's work. We basically take some dynamical system. We take a sampling of measurements, there they are, which are 3 randomly chosen sensor locations. And this is also something very interesting. It's agnostic to sensor placement. As long as the sensor is in a location that's part of the dynamics, Tocken's embedding theorem guarantees you that at the time delay embedded version of it will be able to see the rest of the state of the system under the training procedure. So we take these 3 measurements, we run it through our LSTM, we decode. And here's our loss function, just a simple RMSE. So this is how you would do this. And of course, this actually does a very nice job. But here, if you have a very high dimensional state space, it can be expensive to train. So we did one step further, which is we decided to take the data, compress it using the SVD into a low rank subspace. And now we do the training again, but instead of training to the full state space, we just train onto the compressive representation in the SVD space. So all of a sudden, this is a very cheap training procedure. In fact, you can just train on this laptop in minutes, data like this. So it's not like, okay, once I commit to training, I've got to throw this on some GPUs and wait a bunch of time. This will train in minutes on laptop. So that's something that we really like about this too. It's very fast. So let's see how well it works. Well, the first example here is if you look at the top left, that's the true velocity data for 2D shallow water waves on a globe. And if you look at the middle panel, that's the shred reconstruction by taking 3 randomly placed sensors. Okay. Well, actually, this top one is from mobile sensors. Excuse me. We actually have one sensor moving around. So a single sensor is doing this full job of reconstruction. And here's the reconstruction error. We can not only project it onto SVD modes, we can also use, instead of SVD modes, we can just simply say, look, spherical harmonics are a great basis for this. So why don't we project all the data onto spherical harmonics, which is now still low rank subspace, and do the same reconstruction. And so what you're seeing here is how effective this is as a tool for modeling dynamics of building a reduced model straight from the data. And the data I'm showing you is quite complex. And so we go ahead and step this up, and we went ahead and found some benchmark data sets that are this is from the gallery of fluid motions from APS. And so now this is real fluid flow. So not a simulation, but movies of fluid flows. And on the left is the original video. And the difference between the two videos is one of them is symmetric and one is asymmetric. And when we process the video, here's where the process video looks like. Here's a shred reconstruction of those videos. And the yellow dots are where the sensors are. So we're only listening to 3 locations, and we're constructing this entire state space of the fluid dynamics. We can also, with that same concept, this is work with Stefano Riva from Milan Polytechnic. where we did modeling of a nuclear reactor, a trigonuclear reactor. And what you're seeing here on the left is the full simulations, which are 20 coupled PDEs in open foam. So it's a very expensive simulation. And on the right is our shred model of that reduced model for this. Interestingly enough, what we did here is the only thing you're measuring in this system is the temperature. And from the temperature measurements alone, you actually reconstruct all other 19 fields. So you have 20 fields total. So things like pressure, velocity, ion concentration, all those, I don't measure any of them. All I measure is temperature, and I approximate for you all those other variables, and it's very accurate. So this gives you a pathway for really doing physics for very complex systems under constraints of the fact that you can't even measure these 20 fields, but you can measure temperature easily. So you use that as the measure to map things out to the full state space. Okay, so let's keep going on this. So that shows you that we can build reduced models. And now what I want to do is go back to the latent space. And I want to show you some really fun things you can do in latent space. So I like to call this GoPro physics, because we want to go directly from like filming the physics to learning a model right out of that. And so the way we're going to do that is you first of all have to learn a coordinate system in order to build a good model. So this is work with Mars Gao. And here's the idea. The same basic architecture of shred. And here, for instance, is the data set, sea surface temperature data. I take 3 random measurements. By the way, the number of measurements, if you're in dimension D, you need D+1 measurements. And this is for exactly the same reason you need 3 cell phone towers to localize you in 2D. So you need to be able to disambiguate uniquely. So 3 measurements, and here's what they are. We run them through here, and we reconstruct. But now what we do in the latent space is we impose a loss function to learn to try to find a dynamical system. And the way we do this is with sparse identification of nonlinear dynamics. So this SINDy is a way of learning dynamical systems. And the idea behind it is to come up with a candidate set of right-hand side functions and then sparsely regress onto them. So in other words, I showed you in the 3rd slide that most physics can be represented by very few terms. We're taking that same philosophy here, that the physics can be represented by a small collection of these terms. So you sparsely regress onto a library of candidate terms, and you discover the dynamical system that produced the data you observe. We can either put this, or you can even put something like a dynamic mode decomposition, which is a linear model in that space, which is related to Koopman theory. And so both of these are essentially loss function pieces that we can put into the latent space. So here is what we add to this architecture. We add these 2 terms, the 2 right-hand terms there at the bottom are extra terms to add to the shred architecture. And once you do this, boom. Now, for instance, for the sea surface temperature data, this is the model you find. It's a 3x3 linear ODE modeling the full spatial temporal dynamics. And here are the 3 modes. It's reconstructing all the sea surface temperature data from these 3 modes right here at the bottom. So there isn't a question about interpretability, because we don't know what these 3 modes are. But what this machine learning algorithm did is it found for you 3 modes capable of accurately reconstructing the sea surface temperature data. In fact, if you take this, we can do a rollout for 100 weeks, almost a 2-year rollout. And by the way, this rollout, this 100-week rollout that we have here is an exact solution. It's a 3x3 linear ODE. So we can just write down the solution, project it back out through the decoder. And so you can see it's not perfect, but it has a lot of the right features in a very, very simple model. So we start doing a little bit harder models. So here is a video, flow around the stellar video. There it is. And we said, okay, let's run that through. So put some sensors here, map to a reconstruction, and see what it can find for dynamics. And if you look here, this is what the SINDy model finds. You can pinch the late space to 4 dimensions. You get a 4x4 nonlinear ODE that has a fixed point, which has a limit cycle in it. And this limit cycle, you can run it forward. To solve this ODE, And here's our 180 frame rollout to the future. And we only had 200 frames for training, and we got this model, and now we can just roll out the future and compare it to the real data there. If you want a linear model, you have to go up in dimension. You go up to six degrees of freedom, but now you have a linear Koopman operator that does this approximation. So we went to harder models, and here's one of them. One of them is the shred for turbulence. So what you're looking at as the top is isotropic turbulence. So this is like one of the hardest data sets you could actually take on. And here is our rollout in this shred model for 180 frames in the future of this isotropic turbulence. So this is a very complex data set with lots of spatial temporal features in time and space. And we get this. And what's interesting is what it learns in the latent space is a 16 by 16 linear system of ODEs, and that's the exact solution. So this is kind of remarkable. We took turbulence and we approximated it pretty accurately by this linear model in the latent space. So it's telling us something very important, I think, about turbulence. I didn't think you could do something like this. I just about fell on a chair when Mars showed me this, because this is amazing. I didn't think you'd get anywhere to being able to do something like a turbulence model. And not only can you do it, approximate it, but you have an exact solution because it's linear. So that's a very encouraging result. And then we took that and went to scale. Given that, I worked with Bennett Eximo, here he is. And what we did is we worked with the Barcelona Supercomputing Center. And what they do is they do large scale computations. And what you're looking at here on the left, what you're looking at is the flow dynamics and the heat distribution over the city of Barcelona. So the black things are buildings. So the wind comes off the mountains, blows through the city of Barcelona. And the question is, can you model some of this flow physics? Because if you've been to Barcelona, which I'm sure almost everybody's been to Barcelona because it's such a fun place to visit, you know that if you go in August, you're going to die because it's so hot. And the question, look at all this heat that's captured here. Is there a way for you to engineer the city landscape so that when the wind comes off the mountains, it blows all of this heat over to the Mediterranean? And what you're looking at here, then, we want to be able to reduce model because this is close to 1 billion grid points to do this simulation. And so what we do here is we can take this, and in fact, in the shred architecture, we can compress the whole thing down to 6 dimensions using 3 sensors. So what you're looking at on the right is a reconstruction of the flow physics in Barcelona. And you can see there it's got almost all the right features. There are some errors for sure, but this is building a 6-dimensional space, modeling this very high-dimensional, complex, turbulent flow system. And so we're pretty encouraged that essentially what it's finding for us is the right coordinate system in which to write your dynamics. And so one way to think about shred is this: it's like a one-and-all architecture that does learns a latent representation or coordinate system and compare it with a dynamical system in addition. So this one's a very high dimensional case. I want to show you a low dimensional case. So what you're looking at here is work on bird flight. This is done with Lydia France, who's at Oxford. And I met her when I was on sabbatical, and she was at the Turing Institute as well. And they fly this bird, a hawk, back and forth between these 2 stands. And what you notice is when it takes off, there's a flapping phase, then it glides up to land. So we looked at the flapping stage. And what we did is she had actually strapped up these birds with sensors along both wings, left and right wing, plus the tail, left and right side of the tail. I think a total of 8 sensors. And we basically mapped the small collection of those sensors to the 8 with this SINDy shred architecture and said, can you find me a latent space model? And what you're looking at on the bottom right is a linear 3x3 ODE system that models the flight of this bird. And what you're looking at on the top right, there's actually, if you look carefully, there's 2 birds flapping there. One is the gray and one is the red. The red is your approximation to the gray, which is it's the actual experimental measurement. And the red is running the model through that ODE that I'm showing you there and then matching them up. And you can see you're basically right on fact, this is one of the few models that we have available, generative models for flight. In fact, they don't really have generative models for flight. What people try to do when they model flight is they model the articulation of the wings, the aerodynamics, all these things. But here we go straight from the data to a model. And the shred, this is almost immediate for us. Like we got this result like in one afternoon. And the reason we did it in one afternoon is because we don't have the inversion of trying to build an encoding space and then undo the encoding through an encoder-decoder pair. We decode only, and that's why this works so well. Okay. All right. By the way, for those of you who've trained a lot of neural networks, I want to throw one thing out there. This is the lost landscape across a bunch of data sets. What we found is you have a globally convex landscape. This is like a miracle. I've not seen this in whenever I've looked at latent spaces or the lost landscape of different architectures. It's usually a mess what the lost landscape looks like, and you're trying to find some, local minima or something close to the bottom. But look at these. These are like globally convex landscapes. We don't understand why this is the case, but this is clearly what seems to be the case. Okay. Final part of the talk, I want to talk about this idea of you have models and you also have data and the sim to real gap. So in other words, simulations and reality are very different things. For those of you who do follow Formula One, if you'll remember the last time they did a big rule change, people were modeling, designing cars, doing fluid dynamics, so simulations, and all the cars showed up on the track and they started bouncing, or what are called porpoising, because the simulations they used were not an accurate enough representation of reality. So when they came out and the reality came, the cars behaved very differently than the simulations. And it's created all kinds of problems, actually. And so whenever we have a simulation model, it's an approximation to reality. The question is there a path forward to take our simulation, which typically is some well-chosen approximation, but to close the gap and using real data to close that gap. And so what we do is use a shred architecture to do data simulation. And here's how it works. You have a model. This is your best model for reality. That's the top left here. And you can simulate it. So you can simulate your model. You can simulate flow around airfoils, around cars. But of course, we know that the model is not reality, but we could collect the data. We could build a shred model from it. In other words, map sensors to the full state space. Now, once we train that, we can also say, well, now what I'm going to do is start to engage with reality. In other words, reality is sitting in this gray box in the bottom. We only can observe reality at point measurements, let's say, like at sensor locations. So in the gray box, you don't have access to the full state of reality. Think about the nuclear reactor. Most of the fields in a nuclear reactor, you can't measure. They've never been able to measure them. So you have 20 fields, and you can only measure maybe 2, and at point locations. So what we're going to do, we know we could train with 3 sensors, but suppose I took 20 sensors. I train a shred model with 3 of them, which means I have 17 sensors still out deployed in reality. But I can take my 3 sensors and I can listen to reality and make predictions about what's happening at all those 3 sensors plus the 17 others that I have. And of course, what I'm going to get is a mismatch between reality and my simulation model. And so what you can do, though, with that mismatch is create a gradient descent algorithm so that you update your shred model so that the observations of reality at the 3 locations make the error at the other 17 locations drop as far down as possible. And by updating that, what you've done now is create an environment where you're doing a data simulation. You're taking your model and you're pinning it to the reality measurements, which are only point measurements. So let me give you an example of this. We're going to data simulate. Here's my model. This is 2-dimensional Kuromoto-Shibashinsky. And here's reality. It's the same model, except I have these missing physics terms. So the dynamics are going to be different. So the question is, if I try to make predictions with this, how far do I fall off reality? And so here is what we have. Here's the two columns of this are two different time points. The middle is the real physics. On the left is our simulation approximation if we don't correct it. And you can see I start to fall off. But on the right is using this data simulated architecture to close the gap. And if you notice this, our DA shred, the shred is actually closing this gap. And you can see this further on the right where the blue line, the error starts to just drop. So in other words, as you turn this on, you update that shred model and you pin it to those measurements. And all of a sudden you've got yourself a really accurate model of reality because you've updated the model to reality versus the yellow, which is your model of reality starts to, the error is big and it gets bigger as you go on because it's reality is different than what you actually have in your simulation. So this is a pathway forward to close this sim to real gap and in a pretty fast time frame. If you look at the error dropping down here, it's actually very rapid. You can almost deploy this in real time. So we did this for a rocket engine. So this is a very difficult example. And this is a rotating detonation engine. And so what this is an injector. It's an injector area where fuel comes in. You have ignition, and then you have this shock front as combustion starts. It burns through the fuel, and it starts burning into a region with new fuel as it depletes the fuel. But then there's new fuel that comes into the injector, and what you get is this rotating detonation front. So here's a simulation of this. There's this large pressure wave that comes out. That's your detonation front that relaxes down. And this thing's going around this thing in a circular fashion. So, but we have a model for it, but the real physics is this. It's different than the simulation. In fact, we changed the real physics by adding some terms in one case here or adding terms in a different case here. And so it changes the shock front. And so if you deploy the DA shred strategy, first thing that happens is over time, your error drops. That's the bottom left figure. The blue line comes down and the error drops significantly by an order of magnitude over what if you just use your model. And more of that, you get the right features. If you look on the top right, that DA shred model fattens the wavefront, or in the bottom, it collapses the wavefront to make it thinner. So these are kind of architectures which allow you to, first of all, get closer to the physics. And second, what it also allows you to do is to start thinking, well, what about could I learn the missing physics? And in fact, you can actually do SINDy in this latent space here, and you can apply a SINDy loss architecture to try to learn what would be the missing physics term in that M. In other words, M is the real physics, N is your approximation to the physics. Could I learn an update to N so that my model is more accurate? And so you can do this with the rocket engine. And here's a table across pretty challenging problems. We have 2D KS, 2D Kolmogorov flow, Gray-Scott models. These are reaction diffusion systems, and this rotating detonation engine. And here's all the perturbations or the missing reality terms that we put in. And on the far right is if we enforce this sparsity, we can basically recover the missing physics terms very nicely and pretty accurately. So this gives us a new way to do it. So we're not just discovering physics. You're starting from physics that you feel confident with, but you realize, okay, but I have reality that I have to deal with. And what this is doing is just simply targeting your mismatch between your model and reality. And it could mean learning physics, but it certainly starts to use your sensors to collapse that error down as you go. So I'm gonna end here because I did want to leave time for questions. And these are the three key ideas. It's a very effective strategy. Everything that's here, by the way, you can download code. You can everything's reproducible. I have all the data sets out. You can play around with it. It's not like we cherry pick, like, okay, I trained it once and it worked really well once and I showed you the result. This is really robust and stable under training. And the reason it is because of these key ideas. It's a decoding only strategy, separation of variables, and it's just relying on this idea of Tocqueville's embedding theorem. And this is from the 1960s, this is from 1680s, and this is 1981. So we're almost 50 years of all these technologies being available to us, and now they come together in this one architecture to do some things. If you want more, we made a little YouTube list, a shred YouTube list. So if you look at my name on YouTube and type shred, you'll get access to the YouTube list where it features my various students walking through code. There's also a PyShred package you can pip install that will do all of this. And so I will end it there and take any questions that you might have. Thanks so much.